In this video, we'll talk about the combustion of hydrocarbons, which only have carbon and hydrogen, and carbohydrates, which have carbon, hydrogen, and oxygen. Okay, so let's start with a quick review of what a combustion reaction even is. So some properties. So first of all, it's basically just the burning of some substance. It could be a hydrocarbon or a carbohydrate. Now, in addition to these two things, hydrocarbon, carbohydrate, oxygen is always a reactant, right? You can only burn in the presence of oxygen. And usually it's going to be, or actually always, it's going to be molecular oxygen, O2. The products are always going to be the same two things. They're going to be carbon dioxide, so CO2, and water, H2O. And oftentimes this won't be given to you, so you should memorize this, right? Oxygen is always a reactant, CO2 and H2O are always products. And this isn't a type of exothermic reaction, which means that it releases heat. That makes sense, right? Because all these combustion reactions involve fires, they're exothermic, they give off heat. Okay, so let's look at first the combustion of a hydrocarbon, something that only has carbon and hydrogen, right? You'll notice here that the hydrocarbon reacts with oxygen to form CO2 and H2O. Same thing for the carbohydrate. In both cases, the reactant and the two products are the same. Notice here that for a hydrocarbon, the mass of the carbon initially in the hydrocarbon is ultimately released as CO2. And the hydrogen that was initially in the hydrocarbon is released in the form of water. And then the oxygen goes into both the CO2 and the H2O. This is important because when we do hydrocarbon and carbohydrate combustion reaction problems, knowing this piece of information is critical in solving for the answer. If you look at the carbohydrates, sort of the same thing, right? The mass of the carbon initially in the carbohydrate goes into CO2. The hydrogen goes into H2O. So we have hydrogen, here we have carbon. Now notice one thing, this oxygen now contributes to both the O2 and the H2O, as well as the O2. So these problems end up being a little bit trickier. There's just one extra step. So what we're going to start with is the combustion of a hydrocarbon. Definitely though, for the purposes of your class, you'll need to know how to do both of these. And these are actually very important and they show up on tests very, very often. So let's start with the combustion of just a hydrocarbon. So let's read this example. So it says combustion of a 1.5 gram of a hydrocarbon yields 4.4 grams of CO2 and 2.7 grams of water. What is the empirical formula of this compound? Okay, so here are the steps you have to take. And it's actually very simple if you know the steps, and there's only 3 of them. And we'll do them step by step. The first is determine the grams of carbon in the 4.4 grams of CO2 and the grams of hydrogen in 2.7 grams of H2O. So let's just go ahead and start there. So we know that we start with 4.4 grams of CO2. We can figure out how many grams of carbon are in this 4.4 grams of CO2 by using molar masses, okay? So the total molar mass of CO2, if you calculate this, which I already did in advance, but basically it's just the molar mass of carbon plus the molar mass of oxygen times 2, is 44.0098 grams. Now, for every 44.0098 grams of CO2, you have 12.011 grams of carbon, right? That's the molar mass of carbon. You need to multiply by this ratio in order to figure out how many grams of carbon there are in 4.4 grams of CO2. Okay, so after you do this, you get 1.20083 grams, right? And notice here that my units of CO2 cancel, so I'm left with grams of carbon. I do the same thing for H2O, right? So I know I start with 2.7 grams of H2O. And then what I'm going to do is multiply by that same ratio. So on the bottom, I'm going to write the molar mass of the total, right? And if you calculate the molar mass of H2O, you get 18.0152 grams. And notice here that there are 2 moles of hydrogen per molecule of water. Okay, so I'm not just going to write the molar mass of hydrogen up here, which is the 1.008. I'm going to write twice that because I have 2 moles of hydrogen per molecule of water. So I'm going to take 1.008 times 2. That ends up being 2.016 grams of hydrogen. Okay, this is basically telling us that for every 18.0152 grams of H2O, I have 2.016 grams of hydrogen. Okay, I multiply by this ratio, and I get 0.3021482 grams, right? I literally wrote down every digit in my calculator. Okay, you don't really need to do that. You can round. That should be fine, and you'll get the same answer in the end. Okay, so now we did the first step. Okay, so the first step is done. Let's check out the second one. All we have to do is convert from grams to moles for both carbon and hydrogen. Okay, we know how to do that, right? From this value of grams, we can convert this to moles simply by multiplying. And basically what we're going to write is 1 mole of carbon on the top, and then the molar mass of carbon on the bottom, which is 12.011 grams. Right, we can calculate that later, and then we'll do the same thing for hydrogen, right? For every 1 mole of hydrogen, that's equal to 1.008 grams of hydrogen. And I can solve and put it in my calculator. For my moles of carbon, I get 0.09998. And for hydrogen, I get about 0.2998. Okay? And then if you remember from the previous video where we did percent composition, our rule here is we divide by the smallest number of moles, okay? So here our smallest number of moles is carbon, right? That's our smallest. So we're gonna divide all our values by this number. So for carbon, right, so let's do carbon first. We're gonna take essentially this big number, or it's actually very small, 0.09998 divided by itself, and so we get 1. And then we take we do the same thing for hydrogen. We take 0.2998 all divided by 0.09998. And then that's going to be equal to 2.9986, which rounds to about 3, right? These problems are never going to be perfect because there are errors in your rounding and there's errors in the molar masses. But it's close enough, right? It's very close to 3. That tells us that the molar ratio between C and H is 1 to 3. So my empirical formula is CH3. Notice here that they didn't give us information about the total molar mass, so we can't actually figure out the molecular formula. All we know is the ratio of the elements. So let's do the same thing, but now apply this to carbohydrates. So the question says combustion of 0.25 grams of a carbohydrate yields 0.3664 grams of CO2 and 0.15 grams of H2O. What's the empirical formula of this compound? Okay, let's take a look at the steps. There's just going to be one extra one. Okay, so as before, first step is exactly the same. Second step is now that we have oxygen, we need to use subtraction to figure out how many grams of oxygen there are in the initial carbohydrate. Then the rest is the same, right? You convert from grams to moles and then divide by the smallest to figure out molar ratios. Okay, so let's start with this. So let's start by figuring out how many grams of carbon are in CO2. So I start with 0.3664 grams of CO2. And I'm going to do the same thing as before, where I multiply by that ratio. So I have 12.011 grams of carbon for every 44.0098 grams of CO2, right? Notice that my grams of CO2 are going to end up canceling. Okay. I'm going to do the same thing for H2O. So I have 0.1500 grams of H2O. And my molar mass, right, I write oops, that's a mistake. So my molar mass of H2O is something I write on the bottom. So that's, as we established before, was 18.0152 grams of H2O. And on the top, I'm going to write the molar mass of 2 hydrogens, which is 2.016 grams. Okay, and when I calculate these two numbers, I get 0.1000 grams of carbon, and then I get 0.01678 grams of hydrogen. Okay, so I did the same steps as last time, okay? But now I have one extra element in my carbohydrate. I have this oxygen term, okay? And I need to take care of this oxygen term, okay? And in order to take care of the oxygen term, I'm just going to use subtraction, right? Because I know what I start with. I know that I start with 0.25 grams of a carbohydrate, Now, I know that 0.1 grams come from carbon and 0.01678 grams come from hydrogen, right? I can just take the total, subtract it by 0.1 and 0.1678 to get how much mass is left over from the oxygen. So all I do is take the total, which is 0.25, minus my mass of carbon, right? This is the total, minus 0.1000 grams of carbon, minus 0.01678 grams of hydrogen, and that gets me 0.1332 grams of oxygen, okay? And now when I have all these grams, all I need to do is convert to molar mass, okay? So to convert to using molar mass to convert to moles, okay? So in order to convert from grams to moles, basically divide by molar mass. So I'm gonna basically do 12.011 grams of carbon for every 1 mole. And actually, if you notice here, I did it slightly wrong, right? Because grams should go on the bottom, so my units cancel. 12.011 grams of carbon for every 1 mole. I do the same thing for hydrogen. For every 1 mole of hydrogen, I have 1.008 grams of hydrogen. And then finally for oxygen, right, I multiply. For every 1 mole of oxygen, I have 15.999 grams. Essentially what I'm doing is dividing by all my molar masses. For carbon, I should get 0.008325. For hydrogen, I get about 0.01665 moles. And then for oxygen, I get 0.008327 moles. And then the last step is to divide all these by the smallest, which in this case is 0.8325. These two numbers are essentially the same. This guy reduces to 1. This guy reduces to 1. The middle guy for hydrogen reduces to 2. And so my final answer is CH2O. So that's the empirical formula of this compound.